Hi friends, once again welcome back in our educational channel, that is Precise. Friends, in previous lecture we have studied decade counter, that is mod 10, and in this video lecture we are going to study the next type of counter, that is a ring counter. What is ring counter? A counter in which the bits move in a loop, then it is known as a ring counter. Now the logic diagram of ring counter is going to display on your screen. A ring counter is basically shift register, and in this case it is left shift register because the beats or the clock pulses moves from right to left. That's why it is known as a left shift register. In this logic diagram, it is clear that as we are going to study 4-bit ring counter, so 4 D flip flops are used because in shift register we have to use D flip flop. So in this case also 4 D flip flops are used. The clock input terminal is applied to all the flip flops at a time, and in this case it is positive edge triggered D flip flop because bubble is absent. So it is only a positive edge trigger flip flop. So in this case, the transition of state or bit transfer with positive clock pulse give at the positive edge of input clock pulse. So it is a positive edge trigger D flip flop. The output of first flip flop, that is A, the output is Q0. That Q0 drives the data input terminal of next flip flop, while the output of next flip flop, that is the second flip flop, drives the data input terminal of third flip flop, that is Q1 drives D2, while Q2, that is the output of third flip flop, drives D3. But in this case, the output of fourth flip flop, it is a 4-bit ring count. So obviously the 4 flip flops are used. So output of fourth flip flop is connected as the input for the first flip flop. So output of fourth flip flop is connected back to the input terminal of first flip flop. That means in this case Q3, that is output of fourth flip flop, is nothing but the input of first flip flop, that is D0. So Q3 is equal to D0. In this case, reset pulse, that is a clear pulse, as well as a preset pulse is applied. Second, third and fourth flip flops, in this flip flop the reset pulse is applied or clear pulse is applied, while for the first flip flop the preset pulse is applied. And in all these cases, in all these flip flops, it is a negative edge preset or negative edge set because bubble is there. So bubble indicator is a negative edge. So when clear pulse is applied, clear or it is also known as preset pulse because it is also connected to the preset terminal of first flip flop. So when the clear pulse, when this pulse is applied, then the second, third and fourth flip flop are in reset mode, are in clear mode, but the first flip flop is in set mode. So at the initial stage, before applying any clock pulse, the output of this counter is DCBA is equal to 0001. All 3 flip flops, second, third and fourth flip flops are in reset mode, but the first flip flop, which is in set mode, hence its output is high while the output of remaining flip flops remains low. So output of counter at this stage, at the initial stage, is DCBA is equal to 000. Now when the clock pulse is applied to all the flip flops at a time. So basically it is an example of synchronous counter. It is example of parallel counter. So in this case, all the flip flops are clocked simultaneously. So when the clock pulse is applied, at the positive edge of the first clock pulse, the bit stored in the first flip flop gets shifted to the second flip flop. Bit stored in the second flip flop gets shifted to the third. Bit stored in the third flip flop gets shifted to the fourth flip flop, and the bit stored in the fourth flip flop is fed back to the first flip flop. So bit stored in the first flip flop is already 1, is in set mode, so that bit is shifted to the second flip flop, while the all other flip flops are in reset mode, hence the bits stored in all the remaining flip-flops are low, because all the flip-flops are in reset mode. So at the end of the first clock pulse, the output of counter is DCBA is equal to 0010. 1 is shifted to the second flip-flop. So DCBA is equal to 0010. When the next pulse applies at the positive edge of the second clock pulse, the bits stored are shifted to the left side. So bit shifted in the first flip-flop is shifted to the second. Bit stored in the second is shifted to the third to the fourth, and fourth return back to the first flip-flop. So in this case, the output of counter is now DCBA is equal to 0100, because before applying the second pulse, the output of counter is 0010. That means B flip-flop is in set mode. So at the positive edge of the second clock pulse, that 1 from second flip-flop is shifted to the third flip-flop. So output of counter now DCBA is equal to 0100. At the positive edge of the third clock pulse, when the next pulse is applied, at the positive edge of the third clock pulse, once again bits move towards the left hand side. So the output of counter at this stage is now DCBA is equal to 1000. The bit stored in the third flip-flop, that is a high bit, is now shifted to the fourth flip-flop. So output of counter at the third clock pulse is DCBA is equal to 1000. Next, when the fourth clock pulse arrives, at the positive edge of the fourth clock pulse, once again the bits are shifted toward the left hand side. So in this case, the fourth flip-flop is in set mode, hence the output of fourth flip-flop is high, and that high bit is now shifted to the first flip-flop, because the output of the fourth flip-flop, that is in this case it is the last flip-flop, so output of the last flip-flop is connected to the input terminal of the first flip-flop, hence that high bit from the fourth flip-flop, from the last flip-flop, is shifted back to the first flip-flop. So at the fourth clock pulse, at the positive edge of the fourth clock pulse, the output of counter is DCBA is equal to 0001. So that is our initial stage. That is our first stage. That is before applying any clock pulse, 0001 is our output stage, and that is our initial stage. This counter is known as ring counter. Why it is called ring counter? Because in this case, the bit transferred from one flip-flop to other flip-flops, and from the last flip-flop, it returns back to the first flip-flop. So in this case, bit moves in a circular form. There is a loop, and within that loop, the bit gets transferred. That's why it is known as ring counter. And in this case, the bits moves in the left hand side. So it is basically left shift register. Now friends, a ring counter. What is the application of ring counter? Where the ring counter is used? So ring counter is useful to control the sequence of operation in many digital appliances. It is used to control the sequence of operation, because the bit moves in left hand direction, or maybe moves in a right hand direction. In this case, it is a left hand direction, moves in a left hand direction. So when the high pulse is moved to particular output terminal, a device connected to that output terminal may get active. So it is used to control the sequence of operation. That is the main application of ring counter. Now we are going toward the clock diagram. First of all, as usual, आपण ती clock diagram जी आहे ती study करून बघू how that beats, how that pulses move. So clock diagram of this or timing diagram of this ring counter is now going to display on your screen. ती पहिले आपण व्यवस्थित study करू आणि मग आपण त्याचा explanation बघू. So in this case, the positive edge trigger is there. So the positive edge is indicated by the upward arrow. So there are the clock pulses. 6-7 clock pulses are there. A, B, C and D. A, B, C and D. At the initial stage, before applying any clock pulse, the first flip-flop is in set mode. The preset pulse is applied. So that pulse is given, that is a high pulse. The line is above that alphabet A, while in other cases the line that waveforms is below that alphabet. So A gives a high output while the B, C, D gives a low output. Now at the positive edge of the input clock pulse, the A flip-flop changes its state from 1 to 0, while the B changes its state from 0 to 1. Because the bit stored in the first flip-flop now gets shifted to the second flip-flop, that is a B. So output of B becomes high. Could I? So this is the clock diagram, or this is the timing diagram of our 4-bit ring counter. Before applying any clock pulse, all flip-flops, first flip-flop is in set mode, while the all remaining flip-flop, that is B, C and D flip-flops are in reset mode. So output is now 0, 0, 0, 1. At the positive edge of the first clock pulse, the bit stored in the first flip-flop is shifted to the second flip-flop. So output of second flip-flop becomes high, while the output of second and third flip-flop remains low, because output of B and C flip-flops are low. So state of B and C flip-flop remain as it is. When the next clock pulse applies at the positive edge of the second clock pulse, the output of B or bit stored in the second flip-flop is shifted to the third flip-flop. So output of third flip-flop goes to high level. At the third clock pulse, once again the bits stored in the flip-flops are moved toward the left hand side. So in this case, the bit stored in the C flip-flop, that is a high. C is now in set mode. So output of C is connected to the input terminal of D flip-flop, and due to which the output of D flip-flop becomes high. D flip-flop is in set mode. So at the end of the third clock pulse, at the positive edge of the third clock pulse, the output of counter is DCB is equal to 1, 0, 0, 0. Next, at the positive edge of the fourth clock pulse, the bit stored in the first flip-flop shifted to the second shifted to the third shifted to the fourth, and the bit stored in the fourth flip-flop returned back to the first flip-flop, due to which the output of first flip-flop goes to high level. When the next bit applies, when the next pulse appears, once again the bit shifted to the left hand side, and this process remains continued. So the timing diagram or the clock diagram gives idea, the idea of waveform, how the bits are shifted. That gets clear by using this timing diagram. So by using timing diagram, we can easily understand how the bits are shifted toward the left hand side. So that is timing diagram or clock diagram of ring counter. Now the truth table of ring counter. The truth table of ring counter shows that there are clock pulses and the states of flip-flop, that is a DCBA. Before applying any clock pulse, the first flip-flop is in set mode and remaining are in reset mode. Hence the outputs are DCB is equal to 0, 0, 0, 1. At the positive edge of the first clock pulse, the bit stored in the first flip-flop shifted to the second. So output of counter is now 0, 0, 1, 0. At the second clock pulse, the bit stored in the second flip-flop shifted to the third flip-flop. So output of counter is now 0, 1, 0, 0. At the third clock pulse, the bit stored in the C flip-flop or in third flip-flop is now shifted to the fourth flip-flop. So output of counter is now DCB is equal to 1, 0, 0, 0. At the fourth clock pulse, at the positive edge of the fourth clock pulse, the bit stored in the fourth flip-flop return back to the first flip-flop. So the output of counter is 0, 0, 0, 1. So this process remain continue. The next output is 0, 0, 1, 0, next 0, 1, 0, 0, next 1, 0, 0, 0, next 0, 0, 0, and that is our initial state. So friends, that is ring counter in which the bits moves in a circular form. In a loop, there is a loop. That's why it is known as a ring counter. So friends, thanks for watching this video lecture. In next video lecture, we are going to study next type of counter, that is synchronous counter, or it is known as parallel counter. So friends, keep watching our video lecture. Bye. Take care. See you again.